the least upper. Send this to that collection O. So O union S complement is an open cover for J, because this fellow covers all these things and S prime complex covers the remaining things. Of course, now I have an open cover for the closed interval, closed bounded interval. Done. So then by 3, therefore by 3 or Heine Borel theorem, there exists a finite subcover. Now where will the finite number come from? This will be needed to cover the remaining portion, and some finite number from this, okay. G1, G2, Gn, S prime, these fellows belonging to or J. Now out of this fellow is not needed to cover S. Therefore, these fellows will cover the remaining portion. But clearly, G1, G2, Gn cover S. Because since they cover J, they cover all of S and all of S prime. S prime is covered by this, the S must have come from this portion only. And therefore, I got a finite subcover for it. Therefore, S has a finite subcover. So let me now summarize this. Then summary is that let S be a bounded closed interval A, then every closed set, every bounded closed set in R, and every open cover has finite subcover. Now this is what is essentially the Heine Borel theorem. I will not write it yet as the Heine Borel theorem. Now we will now give a name. A set is said to be compact if from every cover you can extract a finite subcover. So that you can always pack them in finite situations. That's why it's compact. I remember in my days, once upon a time, prehistoric days, when we went as graduate students to the US, we used to carry all our books. Because first of all, we didn't know whether we will have enough money to buy books there. So we had to put all of them, and maybe any damn thing, everybody will carry a pressure cooker and 100 books and lots of masalas and things like that, and you have to pack. So always the thing is how to pack compactly. Okay. And we always just ended up paying a little bit more money in the airlines and being insulted by the Air India fellows and things like that. But today you don't need your books, maybe one thumb drive or one hard disk, you carry everything you want. You don't need your pressure cooker, you don't need your masalas, everything is available there. All you need to probably carry one credit card in the pocket and a backpack and you can travel. Okay, so you are really reached compactness. You are okay, to the ultimate. Maybe it will even increase further. And probably you also can exactly locate in a satellite image where your apartment is going to be and fix it from here and things like that. But we knew nothing. We didn't even know how the country looked like because there's no internet and there's nothing, and there's a one-day orientation program that the United States Information Service will conduct with all movies and things like that, and about US. So compactness the internet is really put the world in the real sense, the compactness. Okay. Just a finite piece, everything is finite. Okay. Now what we have seen, okay, let me therefore give me the definition. This all leads to the following definition. A subset K of R is called a compact set if every open cover has finite. Now what we have proved essentially therefore is, if a set is bounded and closed, it is a compact. So what we have so far, theorem is K is closed and bounded implies K compact. And the converse is also true. It's not very difficult to prove, so I leave the proof as a simple exercise. Also, so that's what Heine Borel theorem. I will call it Heine Borel theorem. That is, a subset of R is compact if and only if subset K of R, if and only if closed and bounded. And surprisingly, I mean, the result is true even 2 dimensions, 3 dimensions, n dimensions. So the result is true, almost essentially the same proof. Well, the result is true even Rn. So basically, therefore, finite dimensional analysis is all essentially same, because the compactness idea is the same everywhere. The real problem starts when you move up in infinite dimension. In infinite dimension, the compactness definition will be the same, or general metric spaces for that matter. The definition of compact sets will be the same, but the criteria will change. It will no longer be closed and bounded, but you will need something like the finite epsilon net property. And that is already there in the real line. They are all built into there, the real line on the finite line. But when you go to infinite dimension, they go apart. Boundedness and the net property are different. Okay. So I will explain this to you shortly, as after I finish. However, this criterion is not true in general metrics. Something more is needed. That more is this epsilon net property, closed and epsilon net property. The epsilon net property is called a name is given called total boundedness. The word we should be very careful when we use adjectives in answering. For example, if somebody asks you whether a function is continuous, and you are so sure it is absolutely, the function may not be absolutely continuous. There is something different. So similarly, when I say bounded, totally bounded. Oh no, that's not correct. Total bounded is bounded. So the terminologies one must be very, very careful. Okay. I will come to this criteria for a general metric space shortly. Okay. let me give you a very simple example. Okay. We already seen what a metric space is. Okay. You have the general set on which you define a notion of distance, or arbitrary notion you can define distance, as long as it satisfies the property of non-negativity, symmetry, and the triangle inequality. Okay. So let's take, for example, a sort of infinite number of points on in the plane, okay, or even in the real life. Okay. So let x1, x2, etc., xn be a countably infinite set of points. And what I do is, I define, so that's my, so let x be the collection of all these points. Okay. Now for xi, xj in x, we define the distance between xi and xj is 1 if I is not equal to j, 0 if I equal to. What I am saying is, I am putting all these points at a distance 1 from each other. Everybody is sitting at a distance 1 from each other. This is possible in infinite dimensions. Take 1, 0, 0, 0, 1, 0, 0, 0, 1, etc. and calculate the Euclidean distance, and the distance is always 1. It's root 2, but you can normalize it. So now, about each point, you take a sphere of radius half, a ball, open ball of radius half. How many points will it contain? The only point which is at a distance half from xi is xi itself. Everybody else is at a distance 1 from it. So, for every j, the ball of radius half around that point is only this point. Okay. So now let us take all these balls. That's now an open cover. Okay. So B of xj, j equal to 1 to infinity, is an open cover for x. Okay. And has no finite subcover. Why does it have no finite subcover? Because if you take a finite number of them, you will get only finite number of points, because each ball is going to give you only 1 point. A finite number of them will give you only finite number of points, but your x has infinite number of points. But is x closed? Is x bound? Okay. These are some tricky questions. Okay. I'll leave it. I'll do more and then come back to this. Now think of a similar example in a slightly different situation. Let us take very specifically L2. What is L2? It is the set of all infinite sequences for which this is finite. All infinite component vectors which are finite Euclidean length. Okay. And now in this we define the inner product of any two vectors as xi yi bar, I equal to 1. The same thing that we do in finite dimension, now we extend it to infinite number of components. To make sure convergence is there, we put that restriction that we are going to look at only those vectors which have finite length. Now, we say x is perpendicular to y if and only if x comma y is 0. Linear product is 0. Two vectors are said to be orthogonal if the dot product is 0. Now, in that, if we now take these vectors, okay, this call is phi 1, phi 2, etc. They are all orthogonal to each other. Their length is 1. Therefore, they are an orthonormal set. Okay. So that's basically this. What I am saying is this always will work. The moment will have an infinite orthonormal set. Now, phi n belongs to n, is an orthonormal set. So, therefore, the length of phi n equal to 1 for every n. So, therefore, it is a bounded set. The whole thing can be embedded in a unit ball. Okay. They all lie in the unit ball. So, therefore, we call this as S. S is contained in the ball of radius 1 upon 0. Including the boundary. Okay. Right? But now, so S is bounded. Is S closed? And the answer is yes. We will see later shortly why it is. A quicker way of seeing it. The answer is yes. Okay. Otherwise, you can argue without all these in topology itself. But then I will show there is a way of looking, another way of looking at closed sets. Okay. Not only from the point of view of the complement being open. There is some other way of looking at closed set. So the set is closed. Okay. So I have a closed bounded set. And it cannot have a finite subcover. If you now draw what is the distance between phi I and phi j. The distance between any two of them is root 2. Okay. So it's root 2. Now what I do, I take phi I and draw a sphere of radius root 2 by 3. Okay. Then what will happen? If I draw around phi j, root 2 by 3, they won't intersect because the distance between phi I and phi j is root 2. Okay. This sphere will take you only up to root 2 by 3 distance. So therefore, I got now the spheres, the balls of radius root 2 by 3 about phi I is an open cover for yes. Can it have a finite cover? It cannot, because every one of them has only one of the phi I points. So cannot have a finite. Doesn't have a finite. So you see now you have a closed and bounded set, but there is an open cover which does not have a finite subcover, which is different from what happened on the real line and Rn. The real line and Rn, whenever you have closed and bounded, the moment you have that, when every open cover will have a finite subcover. That is, the moment you have closed and bounded, you will have compactness. But here, I have closed and bounded, but I don't have compact. So, S is not compact. So, whereas the criteria for compactness in the real line and finite dimensional Rn is closed and boundedness, the criteria for compactness in general metric space is a little beyond that. Okay. It is more than just closed and boundedness. In fact, there are various theorems to look at very classical metric spaces and to characterize that compactness theorem for those particular metric spaces. For example, if you take the collection of all continuous functions on the interval 0, 1, okay, that's a metric space. The metric says that the distance between any two functions is defined as the maximum of modulus of f minus d. F is continuous, g is continuous and closed interval, therefore they will have maximum minimum, so I can define the max of the difference. If you now take that metric space, what are compactness in that space? It is one of the fundamental theorems required in differential equations, the existence theorem. And there is a beautiful theorem called the Arzello-Ascoli theorem, which says under what conditions the set is compact. There is something called equicontinuity, uniform boundedness, and so on. So this closed and bounded will completely appear in different format there. There is something called equicontinuous and uniform boundedness. So there are different varieties of criteria for compactness in different metric spaces, but all of them can be put in one language, namely closed and total bounded. So the only thing that we have to see is what is meant by total bounded in those particular spaces, and that's where all that equicontinuity and uniform boundedness comes into. So I do not know whether I really will get into those theorems, but I will just give the statement of those theorems. Okay. So what I will do next time is look at, I said that this set is closed. I said yes, I didn't give you the reason. I said I look at closed sets in a different format altogether. Okay, and then we will simply, the answer is there, will be staring at our face. Okay. Probably one more class I will look at this particular topological property of compactness, and then I will go to the discussion on continuous functions and semi-continuous functions, and show you about how the optimal value of the continuous function can be found. If you are interested in optimal on either side, then you need continuity, or if you want optimality on one side, lower or upper, then you have the notion of semi-continuity, but all on a compact set. The moment you have a compact set, and that optimal value existence will always be guaranteed. I wanted to tell you about the intersection theorem, but I will tell about the intersection theorem. So one more class about this compactness and all the finishing jobs, closed sets and compact sets. Then I will just do the continuous functions, and then the property of the existence of the optimal value for a continuous function on compact set, and semi-continuous functions on compact sets. So continuity and semi-continuity is what I will do. Then I will get into measure theory. I will quickly go to integration. That's what I had promised that I would do long back. And so I will quickly say why we need measure theory, and what are the things that lead to it, and the standard integration theory, Lebesgue integral. That will be the next part of the course. Up. Yeah. Yes. When I say open cover, it means a collection of open sets whose union encompasses the set. Yeah. No, that is not part. If it is already part of it, then I don't need all the fellows. I will work only with this fellow. My idea is to convert everything to possibly small pieces of open sets, because in topology the building blocks are open sets. So everything is brought down to the building block level. Now what this theorem says is, whenever you have a closed bounded interval, you can always bring it down to finite number of building blocks. That's what this is saying. And the moment you have finite number of building blocks are well understood, and there are only a finite number of them, therefore these are well understood. It's like vector spaces. If you have finite dimensional vector spaces, the building blocks is a basis, there are a finite number of vectors. The moment you know them, you know the whole space. That's the idea. That is the type of idea that you always work. Okay. When I said that I am going to look at closed sets in a different way, it is, see, the topology starts, generally the topological idea starts by defining what open sets are. That is, what are neighbors. The idea of topo means neighborhoods. Okay. How do you study the topography of that space? So you start with neighborhood, that is open sets, and then build everything else as closed sets as a complement and so on. You can actually come the other way around, a closed set, and then complement this open sets and so on and so forth. Okay. So it's like measure theory. We define measure and then define integrals. Then afterwards, wisdom dawns on us. We can say we could have defined integral first and then define measure through the integral. Reverse path. Okay. So they always, if you can see that you go this way, there is a path backwards. The ideas, you can always keep them in mind. It is something parallel to the vector space idea. There I am going to get certain number of vectors which cover the space, and from that I extract finite number of them. That is what a finite dimensional space. So it is somewhat similar to that idea. This compactness is, that's the word compact. The finite number will take care of everything. Finite number of building blocks. And the blocks you can choose. You give any connection of building blocks which will cover this. Out of this I will choose a finite number of blocks which cover this. That's what it is.